Alright, hi Year 11s, this is Mr. Lim here again, and this is our last video on the calculation series in Year 11 about the water of crystallization. So let's get started. Okay, so we're going to work out how to work out the water of crystallization of an ionic substance. So let's find out what that means. So, ionic substances can be hydrated, which means that in their solid form, they have trapped some water molecules inside the lattice. Okay, so the lattice is there are water molecules stuck inside it. So if the water molecules are generally trapped inside at a constant ratio to the ionic substance, so it's not as if it's like full random value how much water goes in. It's like, okay, I'll put a water for every 1 sodium hydroxide or something like that, right? This adds weight to the solid form of the ionic substance and makes it impure. Okay, so that's ionic substances can have water trapped in them, right, and that makes them impure. However, the ionic substance can be anhydrous, which means there's no water, so there's hydrated and anhydrous, meaning that they have all the water removed from the ionic lattice, right? And then the ratio of water to ionic substance is useful information to know because if you can take that ratio and determine the purity of the inorganic substances and stuff, right? And also you can apply that purity to your mass to ensure that you have the right amount of substance for each reaction. Okay, so let's go through the ideas there. Right, here we have an ionic compound. Okay. Okay, an ionic compound, and what we're saying is that there are water molecules stuck in the middle of them. Okay, so they're stuck in the middle of them, but they're stuck at a fixed rate generally. All right, and so what happens is that the substance that you want, the ionic substance, is the majority of the substance. But it also means that there is a small percentage of impurities associated with these. Now, the important thing to realize about this is that, okay, if I go to a lab, or if I go and weigh something out of this ionic substance with the impurities, right, what I'm going to get is that, okay, if say that I calculate that I want 1.2 grams, if I've got my hydrated substance on there, I'm going to have some part of that as water, okay, which is not what you want, because if you want 120 grams of the whatever substance, right, and then you weigh some water, it means that you haven't got enough. What you need to do is add that water to the amount of stuff that we need and then apply it. All right, so that water is sitting there as an impurity which can be solved, but we'll go with that in a moment. So let's have a look at the example. So the ratio of water to ionic substances can be determined in a similar way to empirical formula. Okay, so it's exactly similar to empirical formula, which is where we determine the number of moles of the two substances, the ionic substance and the water, and then determine the ratio between them. Okay, so how do we do that? So let's have a look here. So first things first, you have a look at the data. You see that what they put in is like a little container, heated up strongly, and got rid of all the water that was trapped inside the ionic substance. All right, so looking at this here, this table here, you've got the first one, crucible lid, and copper sulfate at 0 minutes, and then all the way to 20 minutes. And you'll notice that the last two are the same. All right, that's kind of important. Okay, the last two are the same, and we'll go through why. So here, this one here is the crucible and the lid. And that's what it says there, that's fine. So crucible is a container, lid's the lid on it. All right, then you've got the crucible lid and the copper sulfate at 0 minutes, which means that you've got the crucible lid, you've got the ionic substance, the copper sulfate, and you've got the water. Okay, because it's a hydrated compound, you've got both of them there. All right, so as you heat it over time, what's going to happen is that the water is going to be removed from the system. All right, so if you get rid of the water from the system, this is effectively the crucible, the lid, and the ionic substance. Okay, so what you can do is that you can use this value and that value. Okay, so you need to have these two values to work out the mass of the ionic solid, which in this case here is the copper sulfate. Okay, but then we can use this value and this value to work out the mass of water. Right, so each of those values is important to help us get something out of it. Right, so let's have a look at these two things. The mass of the water is equal to 39.71 subtract 37.65, which happens to be 2.06 grams. Okay, and the mass of the copper sulfate is, right, 37.65 subtract 34.00, which is equal to 3.65 grams. Okay, so alright, so now we have the mass of the water and the mass of the copper sulfate. Now remembering that this is very similar to empirical formula, we have to work out then the number of moles of each. So the number of moles of water, which is in red, number of moles of water, which will happen to be 0.114 moles, and I'm going to save that as A. I also have to work out the number of moles of copper sulfate. Okay, so whoops. The number of moles of copper sulfate, which will be equal to 3.65. Nope, no, that's not right. That's the mass of it. Okay, the number of moles is 0.023 moles, which we'll call that as B. And then we can work out the ratio of these two things, or the X, happens to be the waters over the number of moles of the ionic substance, which is the copper sulfate, right, which happens to be A over B, which happens to be 5, or very close to 5. And so therefore, the value of X for copper sulfate is CuSO4.5H2O. Okay, that X being the 5, all right? And that's how you would work it out from evaporation data. All right, here's another question, all right, a little bit simpler. Have a look, have a go. And here's the worked example there. All right, so that's how you go about doing this water of crystallization. And that's it. Adios.